In this video, we have the region bounded by y equals e to the negative x, that's the yellow curve down below, and x equals 1, that's the vertical line cutting off the right-hand side, and y equals 1 over e, so if I plug in x equals 1 for this yellow curve, I end up with y equals 1 over e, that's this line right here, and the y-axis. And then we take this region and we spin it around the x-axis to trace out a solid of revolution. So we have this roughly cone-shaped thing that's been cut off, and it's like a hole has been drilled through it along the x-axis. And you can see what our strategy is to figure out the volume of this thing. We're going to use washers, in other words, circles that have a hole drilled out of them. So we need to find the volume contribution of the washer that's been shown in the picture already. And to get that, I need the outer and inner radii, and then I'll multiply the area of one of these washers by its thickness. The thickness is just a little dx. This washer is located at a position of x horizontally, and that means the outer radius is given by the y value on that yellow curve, which is e to the negative x. The inner radius is just 1 over e because that horizontal line is y equals 1 over e. So we can call that outer radius, we can call it r out. That's variable, that changes with the x position. It's e to the negative x, and then r inner, that stays the same. So the width of the hole we drill in each of these washers is always the same value, 1 over e. And so the area of a washer is given by pi times the outer radius squared. That's just the area of a circle of radius r outer minus pi times the inner radius squared. We can factor a pi out of that and write it as e to the negative 2x. That's what we get when we square e to the negative x minus a 1 over e squared. Now the volume of this little contribution, we're going to call that dv because it's infinitesimal. It's given by this area, pi times the quantity e to the negative 2x minus 1 over e squared, multiplied by the thickness, which was dx. With our volume contribution phrased entirely in terms of x, we're ready to add these up using an integral. So the total volume is the sum of all the volume contributions. And we plug in the expression for our volume contributions. And we add all these up as x goes all the way from 0 to the terminating value, which was x equals 1. I'll go ahead and factor a pi out before I do the antiderivatives. And then I need the antiderivative of e to the negative 2x. And this is a simple chain rule backwards kind of thing. This is negative 1/2 e to the negative 2x. And if you want to verify on your own, when you differentiate that expression, you do get e to the negative 2x out of it. The second term was just a constant, so that integrates to 1 over e squared times x. And then I evaluate as x goes from 0 to 1. When we plug in our upper limit, I plug in a 1 for x, and I end up with a negative 1/2 e to the negative 2. It might be nicer to write that as negative 1 over 2e squared. I plug in a 1 into the second term, and I get a minus 1 over e squared. And then I subtract what I get by plugging in the lower limit, and when I plug in 0 into the second term, that vanishes. But in the first term, I end up with a negative 1/2 e to the 0, which is just negative 1/2 because e to the 0 is 1. So my 1/2 becomes positive. I'm going to move that in front. And then I can get a common denominator on my 1 over e squared terms. I multiply the second one by 2. And I end up with a negative 3 over 2e squared for that term. And that's our final volume for the solid of revolution, and we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.